Dear students, so it's a modified video for the topic energy fluctuations in canonical ensemble, or equivalence between canonical ensemble and microcanonical ensemble, which already we had discussed, and as audio issues were reported for that lecture from almost 10 minutes onwards, I'm just uploading another video. Please see that I am not repeating the first 10 minutes topic that was discussed in the earlier video. And I will continue from almost 10 minutes onwards. So those who are watching this video for the first time, please watch the part 1 of this video or the same topic up to 10 minutes, and please continue with this particular topic, so in order to save time. Sorry for the audio issues. Now, what we were discussing was just the mean square fluctuation of a physical quantity. So we considered a physical quantity represented by some F, and the mean square fluctuation in the physical quantity was obtained. So the mean square fluctuation was obtained as delta EF square the mean. The angular bracket denotes average or the mean. So delta F is the fluctuation in F. So we took the square of the fluctuation and then we took the mean. So that is what we call as the mean square fluctuation in F. So which was obtained as mean of the square of the quantity minus square of the mean of the quantity. So this is what we obtained. So I hope that you have noted the difference. So we named this one as equation number 1. Yes, and I was just asking you or discussing that why do we go after such complicated mathematical procedure like taking the mean square fluctuation. Why we are not satisfied with mere the fluctuation or mere the mean of the fluctuation, to be very precise? Why do you go for squaring the fluctuation first and then taking its mean? And usually you know that we do not end up here, we do not stop here. Finally we take the root of this particular quantity, and we usually take the root mean square fluctuation. See, that's a quite interesting concept that we are using frequently in physics topics. Root mean square fluctuations or root mean square values, and you are familiar with taking of RMS values in many topics like RMS velocity when we discuss the Maxwell's distribution of velocities in kinetic theory of gases, or when you discuss the average value or the root mean square value of alternating currents. Everywhere you are taking root mean square values. So why do we go after that? I hope that you already have understood. Anyway, for the sake of clarity, let me tell you that we take the root mean square value to account for practical to get some values which are of practical interest. For example, suppose that I have a value, I have some physical quantity, say that whose average value, suppose I'm reporting the average value of the physical quantity to be equal to, say, some 5. The average value is 5, and you know that usually in measurements the average value is taken to be the true value, right? So average value is taken to be a representation of the true value. So let the average value of a quantity be equal to 5, and let me write say the individual values, the instantaneous values be x1. So let me say that x1 is equal to 5. Let me say x2, that is equal to 4.5. and let me say x3, that is equal to 5.5. These are the different measurements that I am getting. So say x4 is equal to, say, 4, x5, let me say that is equal to 6, likewise. So these are the data that is with me in the measurement of say a physical quantity, right? Now you know that in order to understand how much this data is varying, what we usually do is that we find out its variation, right? So you can find out what is delta x1. So you know delta x1 will be equal to you can take that x minus x bar. right? Okay, you can take that it's equal to instantaneous value minus average value. So okay, it will be equal to x1 minus x bar. So what will be the value? Okay, x1 minus x bar will be equal to 0. So delta x1. So what I'm writing is now delta x1. Similarly, what is delta x2? Delta x2 will be equal to x2 minus x bar. So delta x2 will be equal to see minus 0.5. You know, here you are going to get minus 0.5. So what will be delta x3? That will be equal to x3 minus x bar. So that will be delta x3 will be equal to plus 0.5, right? Similarly, delta x4 will be equal to minus 1. Delta x5 will be equal to plus 1. Now, if I take the mean of all these delta x, mean of the variation. So what will be the mean of the variation? So I'm just taking delta x bar, that will be equal to the sum of all these values. So you can see that that will be equal to 0 plus minus 0.5 plus 0.5 plus minus 1 plus 1 by 5. So altogether what happens there is this plus 0.5 and minus 0.5 will be getting mutually cancelled away, and minus 1 and plus 1 is getting mutually cancelled away. So what happens finally, you are getting the mean of the fluctuations directly. Mean of the fluctuation directly, you will be getting answer equal to 0, which tells you that there is no any fluctuation at all. Okay, so the mean value, if you take it directly, the mean value of the fluctuation, in some certain circumstances, what may happen that you may get a value which is not practically correct. Okay, so if you take it like this, here it is telling 0, but you know that of course from the data that there has been a lot of variations. For example, there was a 4.5, there was 5.5, there was 4, there was 6. All values were different from the mean value, which is the true value, right? So you can see, when you take the mean value of the fluctuation directly, there is every chance that you are getting a representative figure which is not correct. Okay, so in order to avoid the problem caused due to this minus signs or the algebraic signs, what we are doing, we first square the value, right? Okay, we square the fluctuation. So when you square the fluctuation, what will happen is that the minus sign will be getting say positive, and you square the positive value, you'll be getting a positive. So again, you square the minus 1, you'll be getting plus 1. So what happens there, irrespective of the sign of the deviation, you'll be getting all values represented inside the fluctuation. Fluctuation will values, irrespective of whether it is plus or minus, it will get a representation in the mean square fluctuation. And after taking the square of the fluctuation, means you square the fluctuation first, delta x, you take the square of each of delta x1 square, delta x2 square, likewise you square each of the fluctuation, then you add it, then you take the mean. Okay, so you take the square of the fluctuation, then you take the mean. Okay, you will be getting a representative value. So in order to come back to the original fluctuation, you take the root of the mean. So this is what we call as root mean square value. So this is the same thing that we are going to adopt in this particular topic also. We are going to find out first the mean square fluctuation in the physical quantity F, which can be, the F can be the energy, it can be any other relevant physical quantity of interest for us. So after that, what we will find out is the root mean square fluctuation. Finally, we will end up with the relative root mean square fluctuation in the quantity. Okay, so that is what we are going to do. That now, since our topic is to calculate or to understand the energy fluctuation in the canonical ensemble, see, I'm going to the energy of the system first. Okay, so let's consider the mean energy of a system. Okay, so we are considering the mean energy of a system. So the mean energy of a system in ensemble, of a system in canonical ensemble, is given by, we were denoting it by the letter U. So U is equal to mean of the energy. So this is the way in which we have represented it earlier. So that is given by sum over R ER PR. So this was the equation that we have used earlier while discussing the physical significance of statistical quantities. Okay, so sum over R ER PR. So what is PR there? PR is equal to, which you can substitute for. So that is equal to sum over R. PR, here I am writing it as such, and PR is the famous Boltzmann's equation for the probability. That is nothing but e raised to minus beta ER divided by sum over r e raised to minus beta er. You know what is this denominator? This denominator is nothing but our q. Okay, so this particular thing is nothing but our canonical partition function q and vt or z, right? So this is what we are going to get. So let me say that this is my equation number 2, right? So you got the mean energy of the system. I'm just taking. So what we are going to do, we are remember we are going to take f is equal to u. Okay, so in the earlier equation we are going to take f equal to u. That is what we are going to do. So we have to find out the mean square fluctuation. For that, let's calculate this square of, okay, I'm going to first calculate this quantity. Okay, in equation number 1 I'm going to calculate this quantity. So for that I'm taking, so consider taking square. So consider is the mean e the square. So what will be that one? Simply equation number 2 the square, whole square. So I can write that is equal to equation number 2, that is sum over r. Let's just beautify it. E raised to minus beta er divided by sum over r. Sorry, there is an er here, no? Right, er into, don't, okay, otherwise it will get cancelled. Right? So sum over r e raised to minus beta er. Okay, the whole square. So let's keep it there. Let me call it as equation number 3a. I'm calling it as equation number 3a. Now let's proceed on. So you got this quantity in equation number 1, and now we have to take the mean of the square of, okay, the internal energy. Okay, so here we are taken what? The square of the mean. So this is the square of the mean, right? Okay, now we are going to take what? This quantity. This quantity is what? The mean of the square. So first you take the square of energy and then you take the mean of that. So you know that both of them are different. So we are going to see that one. So therefore similarly, and I'm writing, I'm continuing, and see, this is mean of the square. Okay, and mean of the square, that is given by the same type of relation, that is sum over r er square into pr. Okay, remember that's a way in which you calculate average values statistically. Suppose that you have got a quantity f of r, fr. Okay, you want to find out its average value. So what you have to do is that average value of fr is given by sum over r, that quantity fr times pr. This is a equation. Now if you want to find out the average of the quantity fr square, then the same procedure, only one difference is that sum over r, you have to just take fr square multiplied by pr itself. If you have to take fr cube or just gr, you have to take sum over r, that fr cube into pr, or gr into sum over r, gr into pr. So that is the thing that you have to note. So whatever quantity whose average you have to calculate, that quantity should be taken here. Okay, and you have to multiply it with the pr and take it sum over all states. That's what you have to do. So what will be this one equal to? So this is further equal to, on substituting for pr once again. pr substitute here. So what is that? Sum over r, er square. So that is er square into pr is again e raised to minus beta er divided by q. Q and sum over r. Q then, but I'm just writing e raised to minus beta er. So let me call this is 3b. Okay, this equation is 3b. Now before we are going to use equation number 1. Okay, I have to actually use equation number 1 in order to find out the mean square fluctuation in the energy E or U. Okay, what I'm going to do is that I'm going to consider a derivative. Okay, so that is a deviation from our mainstream of derivation. So we are going to consider, that will be useful for us. Consider the derivative. We are going to consider the derivative of a particular quantity. Consider the derivative dou u by dou beta. Okay, so that is equal to, u is the internal energy, that is equal to dou by dou beta of mean of E, because mean of the energy or average energy is taken as the internal energy for a system in canonical ensemble. Okay, the reason already I have mentioned, because energy is permitted to vary in canonical ensemble. So the average energy is taken as the internal energy of the system, because internal energy is not cannot be taken as a constant. Okay, so that is the average energy is taken as the internal energy. So dou by dou beta of eta sorry, of energy. So that is equal to dou by dou beta, okay, dou by dou beta of energy, no, okay, mean of energy. So you know that is, what is that? That is sum over r er e raised to minus beta er divided by sum over r e raised to minus beta er. So that is your average energy or mean energy, okay, which you know from which equation? From this equation, equation number C2, from equation number 2, that is using equation number 2 that we have written here, right? Now look at this expression. You have to take dou by dou beta, partial derivative with respect to beta ആണ് നമുക്ക് എടുക്കേണ്ടത്. So you can see in both the numerator as well as the denominator you have terms containing beta. So here is there is a beta term, here there is a beta term. So you can do it either by the quotient rule of differentiation or the product rule of differentiation. So what I'm going to do is that I'm going to use the product rule of differentiation. Okay, so I will consider the numerator as u, okay, and the denominator, not the denominator, 1 by the denominator value as v. So I'm going to consider it like this, and I'm going to use the product rule. You know, product rule and the quotient rule, they are actually equivalent, so you can consider it either way. So that is equal to, so I'm going to write this is equal to okay, so v du plus u dv, that way we are going to write. Okay, so v du, v is what taken as 1 by sum over r, 1 by the denominator, that is 1 by sum over r. You can write as q actually, e raised to minus beta er, that is your, okay, v, this is my v, 1 by of that, okay, times derivative, no, okay, v du, so derivative of the numerator quantity, so that is dou by, that is dou by dou beta of, dou by dou beta of okay, the numerator, that is what, sum over r e raised to minus beta er, okay, then plus see, I can write u dv, that is what, sum over r numerator e raised to minus beta, sorry, er, there is, okay, actually here also there is a er is to be multiplied, see, er e raised to minus beta er, right, okay, into dou by dou beta of the v is what, 1 by sum over r, that is q, e raised to minus beta er. So this is what we are going to get. So let's just solve it. So it's not so complicated because it's an exponential function. So it will be equal to, see, the denominator I am keeping it as h, that is sum over r e raised to minus beta er, that is there in the denominator. So in the numerator what will happen is that, you know, okay, so it is with respect to beta. So only the beta term will be just getting affected. So what will happen, that coefficient of beta will be also getting multiplied. Er നമുക്ക് already പുറത്തേക്ക് എടുക്കാൻ പറ്റും. So that will be equal to, finally what you are getting, you'll be getting a minus er എന്ന് കൂടുതൽ വരും. ആ er ഉം and the other er will be getting multiplied. So you are going to get this one as minus sum over r minus sigma r sum over r er square e raised to minus beta er. That is quite simple, I think. Okay, anybody can understand that. Plus, what's the next thing? See, what's the next thing? See, it is just a dou by dou beta of, first term is already there, it's dou by dou beta of 1 by that term. So what will be that 1 by that term? That will be 1 by derivative of 1 by x is 1 by x square, right? Okay, so just what happens there is like, see, I'm writing sum over r e raised to, sorry, er times e raised to minus beta er, that is already there. This is what I have written, times the derivative of the next factor, so that will be equal to okay, minus 1 by x square, right? Okay, so it will become into minus 1 divided by that term whole square, sum over r e raised to minus beta er the whole square. First you have to take function of function rule, then into okay, into sum over r, what will be the thing, e raised to minus beta er multiplied by minus er, okay, minus er, I have to take function of function rule. So this minus and this other minus will get positive. So what you are left out is first term I am writing as such, okay, that is minus sum over r er square e raised to minus beta er divided by, I am writing the denominator as sum over r, same, e raised to minus beta er, then this minus and this minus has made the second term also positive, so that is equal to plus. Okay, what is there? Can't you see that it's a repetition? The same time is getting repeated. Okay, so it's actually into multiplied. Okay, same time is getting repeated twice, so that will be equal to, and the denominator is already a square, so that is sum over r er e raised to minus beta er divided by the q. Q is what? Sum over r e raised to minus beta er. I can write whole square. So now before we proceed on, I think you can see that this is a familiar term. See, you can see this equation, this term, this particular term, okay, is nothing but 3b. It is nothing but 3b. You can see that the er square term is here. Here is there is er square term also there in the, okay, here. So that is nothing but mean of the square of energy. Mean of the square of energy. Similarly, on a close look, you can see that the second term here is nothing but our what is given by 3a. Is not? This is the actually 3a, which is nothing but the square of the mean. 3a. So now I'm going to substitute both the things here. So this is nothing but, this is what we have established. This is nothing but minus of, okay, square of the mean, minus of square of the mean plus, right, mean. Okay, sorry, the reverse way, right? Okay, so this is this one is e square, right? Pardon. Let me just correct it. Yes. So this one, first term is okay. See, mean of the square. So I have to take square. I have to take okay, yeah, mean of the square plus the second term here is what? Square of the mean, right? So this is the thing. And what do you have on the left side? Left side is dou u by dou beta. Dou u by dou beta. So let me continue. So therefore, on inverting, what you can get is that see that is dou u by, I'm continuing, dou u by dou beta, that's equal to so you can just see that you can write this one as minus, I'm repeating it here, so e square, then plus the square of the mean, which is nothing but minus of mean square fluctuation as per equation number 1, minus of the mean square fluctuation in energy. Okay, mean square fluctuation in energy. Okay, so I can therefore we need the mean square fluctuations. That is why therefore I'm rewriting it as inverting LHS and RHS. So that is mean of square of fluctuation in energy, that is equal to minus dou u by dou beta. Okay, minus dou u by dou beta. Now what I'm going to do, that's why we have taken this particular derivative. We consider this derivative because of this particular relationship. Now what I'm going to do is that, hope you remember we used one identity earlier. Okay, that is the dou by dou beta. Dou by dou beta, that was proved to be equal to minus kt square dou by dou t. Minus kt square dou by dou t, because beta is equal to 1 by kt, the inverse temperature. So you can just prove this one. We already have proved in some earlier steps. Okay, you can use this identity. You can remember this one as an identity to skip many of the steps. Dou by dou beta is equal to minus kt square dou by dou t. So here I'm going to use that one. So here you have got minus dou by dou beta. So I can write this one is equal to, this is equal to simply kt square dou by dou t of u. Kt square minus is getting cancelled. So that is kt square dou u by dou t. Okay, let me call this one as equation number some, okay, see 4 or 5, whatever it is. Okay, so let me call this one as equation number 4 for the time being, right? Yes, so that is the thing. Now for an ideal gas system, but for an ideal gas system, ideal gas in 3 dimension, you have the expression for internal energy. Already we know that's a classical result. That is what? U is equal to simply 3 by 2 nkt. For an n particle system, that is 3 by 2 nkt. Let me call it as equation number 5. So now you can substitute this u in expression number 4. Therefore, we will be getting the mean square fluctuation in energy. The mean square fluctuation in energy of the system in canonical ensemble is equal to kt square into dou by dou t of u. So what will be dou by dou t of u? That 3 by 2 nk is not 3 by 2 nk. Is it clear? 3 by 2 nk. So which can be again simplified as 3 by 2. We can rearrange it nk square t square, right? 3 by 2 nk square t square. Let me call it as equation number 6 or something like that. Okay, so you got the mean square fluctuation in the energy of the system in canonical ensemble. Now you know, rather than the mean square fluctuation, we are interested in what you call the relative or the root mean square fluctuation, that too relatively. Okay, so we are going to take the therefore relative. Think of why we are taking relative root mean square fluctuation. So this is the quantity of physical interest in energy of the system. Relative mean square fluctuation of the energy. We are writing it as what? First I am taking root mean square fluctuation, that is delta E square mean then root. Okay, when you write, you know that when you write RMS, we do it in the reverse sense. First you take the square of the fluctuation, then take its mean, then you take its what? Root. That is what we call root mean square. The procedure is just the reverse of what you tell. Root mean square fluctuation. Okay, so we have to take, I'm taking the relative root mean square fluctuation. What is my relative root mean square fluctuation? You have to divide it with what? The actual true value, which we are taking as the average value. Okay, already I have mentioned the true value of the quantity is usually considered to be mathematically equal to the average of the quantity. Okay, അതുകൊണ്ടാണ് നമ്മൾ എപ്പോഴും ആവറേജ് എടുക്കാൻ കാരണം ആവറേജ് വാല്യൂ ആണ് ട്രൂ വാല്യൂവിന്റെ റെപ്രസെന്റേഷൻ ആയിട്ട് നമ്മൾ എടുക്കുക. So why do we go for relative root mean square fluctuation? That should be very clear. For example, I can make it clear by an example. Suppose that some quantity, certain physical quantity, x in the average value, okay, average value എന്ന് പറയുന്നത് അല്ലെ ട്രൂ വാല്യൂ എന്ന് പറയുന്നത് say that is 100. Okay, x1 bar. Okay, some quantity. Sorry, I can take x itself. Now, suppose you are getting the mean root mean square fluctuation. നമുക്ക് കിട്ടുന്ന root mean square fluctuation in x in the RMS value, root mean square fluctuation value കിട്ടുന്നത്. Suppose that is equal to okay 1. Right? Now you have got another quantity similarly y bar. Y യുടെ root means okay no value അതിന്റെ actual value 1000 ആണെന്ന് കരുതുക. ഓക്കെ, അവിടെ നമുക്ക് എന്താണ് വൈയിൽ ഉണ്ടാവുന്ന റൂട്ട് മീൻ സ്ക്വയർ ഫ്ലക്ച്വേഷൻ കിട്ടുന്നത് നമുക്ക് 1 ആണെന്ന് കരുതുക. ഇതിൽ ഏത് റൂട്ട് മീൻ സ്ക്വയർ ഫ്ലക്ച്വേഷൻ ആണ് ഓക്കെ വലുത് എന്ന് മനസ്സിലാക്കുമ്പോൾ നമുക്ക് എക്സിൽ ഉണ്ടാവുന്നതും 1 ആണ്, വൈയിൽ ഉണ്ടാവുന്നതും ഫ്ലക്ച്വേഷൻ 1 ആണ്. പക്ഷേ നമുക്കറിയാം 100ൽ ആണ് 1 ഡിഫറൻസ് ഉണ്ടാവുന്നത്. സോ 1 okay part is actually okay, one part of this fluctuation is happening out of 100. But in the case of y, you can see that one part of fluctuation is occurring in out of what 1000. അപ്പോൾ 1000ൽ ഒന്നാണ് ഇവിടെ ഫ്ലക്ച്വേഷൻ, ഇവിടെ 100ൽ ഒന്നാണ് ഫ്ലക്ച്വേഷൻ. അപ്പോൾ നമുക്ക് in order to understand how much is the actual fluctuation, you have to go for what is known as what? Relative fluctuation. So this is the same concept what you are doing when you calculate the error calculation. No errors in calculation. No, you know what we are interested is in the what you call is the relative. Sorry for the disturbance. The relative errors in the quantities is what is of more importance. Okay, so here I am taking the relative root mean square fluctuation in energy. So, and you will get here that the relative mean square fluctuation is equal to that's equal to, I can just divide, I have to take the root of equation number 6, that is 3 by 2 n k square t square. Okay, divide by see what is average energy, that is 3 by 2 okay n k t. So you know what is going to happen is that this kt and kt will be getting cancelled, on taking square root, that will be getting cancelled, and see, of course, there is a root n in the numerator and there is a n in the denominator. What will be remaining is what? Of course, you can see that there will be a root n in the denominator, and 3 by 2, root 3 by 2 and 3 by 2, there will be a root 3 by 2 in the denominator, which I can write as what? Root of 2 by 3. So what's finally left out is root of 2 by 3n. Root of 2 by 3n, and 2 and 3 constants. So I can say that finally the relative root mean square fluctuation in energy of a system in canonical ensemble is directly proportional or inversely proportional to root of n. So what is n? N is the number of particles in the system, and to know this is something quite significant. This is our conclusion. We are going to conclude the discussion right here. So you can see that this we call it as equation number 7. Therefore, the relative root mean square fluctuation in the energy of a system in canonical ensemble is inversely proportional to the number of particles in the system. And you know, the number of particles in any statistical system is of the order of minimum Avogadro number, okay, which is pretty high. Okay, and this is what we call as the thermodynamic limit. In the thermodynamic limit, the number of particles of the system is tending to infinity, which means a very high value of the order of Avogadro number. So what will happen is that since the relative root mean square fluctuation in the energy is inversely proportional to the number which is so big, what will happen? The fluctuation becomes practically negligible. So the fluctuation in the energy is what? Practically negligible, right? So that's our conclusion. The relative RMS fluctuation energy of a system in canonical ensemble is quite negligible, okay? And thus, for all practical purposes, a system in canonical ensemble has energy equal to, or we can say almost equal to, the mean energy U. Okay, so remember one thing. We started by stating that the energy of a system in canonical ensemble can vary anywhere between 0 and infinity. Okay, but when we consider the relative root mean square fluctuation in the energy of a system in canonical ensemble, we find that that fluctuation is inversely proportional to the root of what? The number of particles in the system. And see, n being so large, like Avogadro number, this relative RMS fluctuation in the energy becomes what? Quite negligible, which means that there is no practical fluctuation in the energy, even though it is permitted theoretically. Okay, and artham idana namukku ariyan manasayundavum, practically canonical ensemble energy vary cheyan vendi nammal permit cheyyunnundengil polum, ഓക്കെ, നമ്മൾ തെർമോഡൈനാമിക് ലിമിറ്റിൽ സിസ്റ്റത്തിൻ്റെ പ്രോപ്പർട്ടി പഠിക്കുമ്പോൾ ഈ ഫ്ലക്ച്വേഷൻ എന്ന് പറയുന്നത് വളരെ വളരെ നെഗ്ലിജിബിൾ ആണെന്ന് കാണാം. അതിൻ്റെ അർത്ഥം എന്താണ്? എനർജി ഓഫ് എ സിസ്റ്റം ഇൻ കാനോണിക്കൽ എൻസംബിൾ ഈസ് പ്രാക്ടിക്കലി റിമൈനിങ് വാട്ട്? കോൺസ്റ്റന്റ്. ഓക്കെ, പക്ഷെ നമ്മൾ കണ്ടു എനർജി ഓഫ് ദ സിസ്റ്റം കോൺസ്റ്റന്റ് അല്ലെ. മാക്രോ സ്റ്റേറ്റ് EVN ആയിട്ട് നമ്മൾ എടുത്തത് ഏത് എൻസംബിൾ ആയിരുന്നു? വിച്ച് എൻസംബിൾ വാസ് ഹാവിംഗ് മാക്രോ സ്റ്റേറ്റ് E equal to constant? It was microcanonical ensemble. Okay, so you can see that in the thermodynamic limit, the results obtained by microcanonical ensemble and that of the canonical ensemble is actually coinciding. Means the two ensembles lead to practically identical results in the thermodynamic limit. Okay, that is why this particular topic of energy fluctuation in canonical ensemble is also given as equivalence between canonical and microcanonical ensemble. So from the consideration of energy fluctuation of a system in canonical ensemble, we could establish the equivalence between canonical and microcanonical ensembles. Okay, and when we introduce the ensemble formalism, I had already mentioned that later we will prove that all these ensembles are what? Practically giving you the almost the same result in the thermodynamic limit. So that gives you the relevance of thermodynamic limit considerations in statistical mechanics. Not only that, based on convenience, based on the mathematical convenience, you can treat a system either as a member of canonical ensemble or as a member of what? More ideal microcanonical ensemble. In the thermodynamic limit, all these results will converge. Okay, so that's about it. Please read more, and we will be discussing a similar topic in grand canonical ensemble. And in grand canonical ensemble, let me give you a hint. The macro state is TV mu. Means we permit energy to vary means energy can vary in the case of grand canonical ensemble. It's an open system now. Both energy and number can vary, and also number can vary. So there will be two types of fluctuation as far as a system in grand canonical ensemble is concerned. One is energy fluctuation, which will be treated very quite similar to what we have done now, and we have to additionally treat the fluctuation number. So there will be energy fluctuation as well as what, number fluctuation for a system in what, grand canonical ensemble. And we will be concluding almost the same thing, okay, in grand canonical ensemble in the thermodynamic limit. The fluctuation in energy as well as the fluctuation in number will be negligible. So the result of grand canonical ensemble approach also will be coinciding with other approaches. Okay, so that's about it. Thank you.